Hey everybody, welcome back to another round of engineering, and yeah, let's get at it. The next thing that I will review briefly is based off of, I'll say, energy conservation. Energy conservation in circuit. I think this is the best way to say it. Now, generally, electrical engineers, or just in electronics in general, we don't tend to think about energy as much. Okay? And I'll give you an idea. We'll start off with energy conservation. En equals E out, energy out. Okay? But the name of the game is not necessarily how much energy you have, but also how quickly can it be produced. Okay? For example, if I have 40 joules of energy, but it takes me 10 years to produce that energy, I can't do anything useful with it, right? Now, if it takes me, rather than 40 joules and it takes me 10 years to use it, maybe if I use it in 1 second, now I can actually do something useful with it. So the name of the game generally in electronics is not necessarily energy, how much energy I have, but also how quickly it can be produced or expended. So you can kind of see where this is going. Rather than energy, generally you'll see discussions about power. Cue the music. I've got the power! So rather than thinking about energy in and energy out, let's think about the energy per unit time. In other words, the energy per unit time going in. And because I have an equation from energy conservation, that must be the energy per unit time, which is flowing out. And so we end up with something that the power being delivered to the circuit must be the power being expended by the circuit. So oftentimes you will not see energy conservation. You will not see the energy being inputted is equal to the energy being outputted. Okay? Rather, you'll see it expressed more in terms of power. Okay? The power delivered by the battery is expended by the resistor, for example. Or the power being delivered by the battery is being used by the load that's withdrawn from the circuit. So that being the case, we should also highlight what circuit element actually removes energy from the circuit. So we start going and racking our brains and we say, well, a capacitor, well, no, a capacitor stores energy. It's an energy storage device. Energy in the electric field. Or you could say something like an inductor, and I say, no, that stores energy in the magnetic field. Of course, you probably hit on this already. You already knew. It's the resistor. The resistor is how we remove energy from the circuit. So we better talk about how do we calculate the power of a resistor. Let's go back and think about the energy. We'll use energy to get the expression for power. So let me ask you this. If you have a charge Q and it moves from one side of a resistor to the other side. So you imagine a charge Q coming in on a wire and it moves from one side of the resistor through the circuit to the other side. As it does that, as it moves across the resistor, it experiences a drop in potential. A drop in electric potential. First question for you. What's the change in energy? You got it? So I'll put the change in energy, or maybe I should say the energy expended, the energy lost is given by the charge times the potential difference. Okay. There's a relationship between the electric potential energy, which is what I'm using over here. Maybe it would be more accurate for me to use U. There's a relationship between the electric potential and the electric potential energy. Okay. Now let's go ahead. Let's take a time derivative of both sides. So I'm going to move from my delta notation. I'm going to move into a differential notation. Okay. And over here, we do something like, okay, well, the potential drop across the resistor stays the same. And so you end up with something like this, dq dt times my change in potential. And again, I'm just going to drop the change side. I guess you could leave that one in there, but. And now again, we've decided that this is power, which we represent with P. And over here, dq dt, that's just my current, I. So I end up with something that says the power, the energy removed per unit time by the resistor, so maybe I should put an R in here, the power, the energy removed per unit time by the resistor is the current flowing through the resistor times the potential drop across the resistor. Okay? Of course, this is one way of writing it. A different way, so I'll box that. That's a review thing that you need to remember. Another thing would be, hey, instead of writing this as the potential drop across the resistor, I could apply Ohm's law. I can use Ohm's law, which gives a relationship between the potential drop across the resistor and the value of the resistor. Ohm's law gives you the relationship. So we can plug Ohm's law in, and so you could write the power of the resistor, how much energy per unit time is removed, as being I squared R. So there's another way of doing it. And that really is the function of the resistor in a circuit. It is to take energy from a source and remove it from the circuit altogether. Now, when I say remove it, okay, so when we're dealing with circuit diagrams, you have your battery, you have your resistor, and then you complete your circuit. Okay. Please bear in mind, this resistor could be a light bulb, right? The resistor is a model. It's a way of removing energy. Physically, it could be something like a light bulb. That is the world's worst light bulb. But physically, it could be something like the light bulb. Or maybe it's something like, I don't know, a motor. Okay. So it could be a motor to spin a CD. Or maybe it's, something like a touch screen on your phone, something. It doesn't matter from a modeling standpoint. We don't really care. Okay, we just treat those all as if they were resistors. They're removing energy, taking energy that's stored in the battery and removing it to do something useful. Okay, so that's the brief review on power. Now, along with that, engineers use that idea a lot. Okay, they make sure that when they analyze their circuit, they have a balance. The power in is equal to the power out. Okay, this would be a very good sanity check. What do I mean by that? Let's say that you have gone through and analyzed a circuit. No, I'm just drawing something in here right now. Let's say you go through and you analyze a circuit, R1, R2, R3. You have a battery. And we'll review Kirchhoff's laws in another video. But let's say you've gone through and you found the current running through all of the parts of the circuit. So you know all the I's. One sanity check would be to make sure that the power expended by the resistors is equal to the power being generated by the battery. Right? You want to make sure that the power of resistor 1 plus the power of resistor 2 plus the power of resistor 3, R3, is equal to the power being generated by the battery. Okay. So it serves as a good sanity check. You go through, you find all of your currents, then you go back and double check to make sure that the power is balanced. Associated with this idea is what is called the passive sign convention. Now, I will emphasize here, okay, the passive sign convention comes into play. It is useful when you are looking at the balance of power. Okay? When you're actually trying to compare the power expenditure to the power input. Okay? The energy being expended and the energy being provided. Okay? So that's the only time you have to worry about this. So when you're doing your circuit analysis, don't have to worry about it. Okay? It's only when you're thinking about the powers. And the passive sign convention simply helps you know which side of the equation to put an expression. Okay. Do I put it on the, I guess I call it P in, but I could say P provided, or do I put it on the power expended side? Okay. What the passive sign convention says is, is that if current runs to the positive terminal. Okay. If current runs to the positive terminal, then put it on the P expended side. If it goes into a negative terminal of a battery, for example, then you put it over here. So it helps you know which group it goes in. Is it being expended or is it being provided? Now, the book presents it slightly differently, but I assure you that the conceptualization is the same. Okay. I think it says, I believe the book says, if your current runs into, say you have a battery, for example, if your current runs into the positive terminal of a circuit element, there we go, sorry, I was struggling for the word there. If it runs into the positive side of a circuit element, then it's positive power. Okay, so power greater than 0. And if it runs into the negative side, the negative terminal of an element, then the power is negative. Okay. And again, if you just simply say, okay, well, the power of each of these things, and you add it up, taking the sign into account, then you'll still end up with the same thing. So it's just a way, it's a bookkeeping measure. Okay, so let's go ahead and run an example problem. Now, since we haven't done Kirchhoff's laws yet, I'm just using a simpler problem just straight from the textbook. But we'll try a couple of extra times after applying Kirchhoff's law and check that the power is actually balanced. Now, right here, there is a little bit of ambiguity. I assume right here, this unit 1, I believe this is a 24. But if it's not, we'll know once we check the power being generated and the power being removed from the circuit. So go ahead. Here is a circuit. Now, we're not told what these elements 1 through 7 are. They might be resistors, they might be batteries. From that standpoint, since we're analyzing the power, it doesn't really matter what these things are. Okay, they're some sort of black box, which is why they put boxes in. Go ahead, take a minute, see if the power is balanced using this as 24. You got it? Good. Okay. So we have a couple different ways to do this. I'm going to go ahead. We'll just say, okay, this is another way of writing the power. So the sum of all the powers in the circuit is equal to 0. And we can use, for example, the passive sign convention to determine whether I should put a positive or a negative sign in front of each of these terms. The other way to say it, if you wanted, you could say the power produced must be equal to the power expended. I think that's what I did in the last slide there. Okay. I'll go ahead and do it this way just to give you a different flavor of what's going on. So let's get rid of that. Okay. So we go through and we have 7 different circuit elements. So technically I should put down this 7 times. We have P1, P2, and I'm writing this out right now just so that we can explicitly put in the signs using the passive sign convention. P7, there we go, equals, and I'll put a question mark in here because this is what we're checking right now. And now let's go ahead and go through and assign whether we should be putting a positive or a negative sign. So I'll go ahead, I'll start right here, and nicely the problem has given us direction of the current in the branch that contains element 1. So we see that, okay, so it leaves the positive terminal, and so that means that it must be entering the negative terminal. And by the passive sign convention, if it is leaving the positive terminal, that means that we should have a negative sign there. So I'll put a negative sign in front of P1. And now let's go ahead and walk around the loop. We'll keep going, and we see that because this location right here, that right angle in the upper left corner, that is a node, not an essential node, a node. So the current flowing through circuit element 1 must also go through circuit element 2. So I'll go ahead and draw that in. So we still have that current going in here. And since it's entering the positive side of that element, then we should have a plus here. And now we keep going. So we keep going, keep going, keep going. Uh-oh, now we have this node. And I've circled it. That is an essential node. You notice there's more than 2 wires coming from this, this junction, for lack of a better word. So that one right there is an essential node. So we have a split in the current, if you will. Well, let's go ahead and look at element 3. If the current is coming in and it tells us again that it's moving down the wire, okay, so I draw that in, right? We're given it right here. So it's entering again the positive side, so we better put a positive there. And if I look at element 4, same thing. It's going into the positive side, so we've got a positive. Keep going. Element 5. Let's see. We're told that in that horizontal wire, the current is moving from right to left, and therefore the current is actually entering the low side of whatever this element is. So we have to put in a negative sign. So there's the negative sign. And then they recombine. Again, keeping in mind there that right and left hand nodes, those are both essential nodes or extraordinary nodes. Let's looking at element 6. Current's going in the positive, so we get and you should get a feel for this. You probably have an idea here. Element 7, again, it's positive. So there we go. Now we can go ahead and use the relationship between the power of a given circuit element, relating it to the current flowing through that element, and the potential drop across that element. Oh, good, great. Oh, no, we're okay. I was using capital letters. We're okay there. So let's go ahead and use this relationship between the current, the power, and the potential and substitute in. And in fact, we'll just do that multiplication. We have negative 5 times 24. Go ahead, go. And I will be quiet and you can write it in as well. And make sure you don't accidentally drop those signs. Okay, good, good, good. If you're not done, go ahead and pause. So what I've written down is I have written first the current, and then in parentheses, I write the potential drop. So it's always good after you've written everything. Oh, here I've made a mistake already. It's always good to go back and check yourself. So you notice this third one, I made a mistake. I was writing down the number associated with the element, not the potential drop across the element. So this one would be an 8, not a 3. Okay, so 4 amps. So it's always good to go back and double check yourself again. Of course, I probably don't do that enough, right? You guys catch all these mistakes. Okay, there we go. So now let's go ahead. Yeah, I mean, now we're just stuck with adding together a bunch of numbers. There we go. And so what do we have? Well, 120 plus 30, so that gives us a negative 90. Negative 98. Of course, we see that this 8 and that 8 cancel, so maybe we should not even worry about that. We'll just cancel those two suckers out right away. So we have 30 plus 30, and then 48 plus 12, so that gives us 120. And of course, we have that negative 120 there. So we get, oops, excuse me. Well, yeah, we'll put it this way. So we get 120 plus 120, which is clearly equal to 0. So indeed, apparently, even though it was cut off, I apologize for that, indeed, this looks like it was 24 volts. And in fact, we could have, you could do that again. Of course, we could have just ignored what that voltage is altogether. Said if power is balanced, then what's the value of the potential drop across that resistor or battery, whatever that is, that element. Okay? So, for right now, I'll leave it there. But as I said again, after we do Kirchhoff's laws, I get that reminder for you, this will come back. We'll use this as a sanity check several times when we're applying Kirchhoff's equations. Okay? So keep that in mind. That's all I have for you right now. Keep practicing, and I'll see you next time.